Okay, thank you. Thank you very much for having me here today at this really great event. Today I'm going to talk about tropical cyclones and climate. And I want to motivate this a little bit by the fact that tropical cyclones have been in the news a lot recently, affecting us here in Florida, including other parts of the country. And so in particular, in the last 2 years, we have had 4 Category 4 Atlantic hurricanes to make landfall in the United States. And so these are storms that are some of the most intense hurricanes that you can have. And so those 4 storms are Hurricane Harvey, which made landfall in Texas last year and ended a 12-year span of not having any major hurricanes making landfall. And so they kind of came roaring back to life. And Harvey then proceeded to spend several days meandering along the Texas coastline here and dropping several feet of rain over the Metro Houston area. After Harvey, last year there was Hurricane Irma, which was a very long-lived storm that had peak winds of 180 miles per hour and wreaked havoc on the Caribbean islands, such as the Virgin Islands, at that intensity before making landfall as a Category 4 storm in the Florida Keys and then coming up the Florida Peninsula. So I'm sure you all remember getting the outer bands of Irma here last year. Then a short time later last year was Hurricane Maria, which really devastated Puerto Rico. It's more than a year later now and they're still not recovered there. And then, of course, most recently, hitting very close to home here in Tallahassee, Hurricane Michael, which was actually the 4th strongest hurricane to ever make landfall in the continental United States and was the strongest ever to impact the Florida Panhandle. So for us, it was pretty unprecedented, and we know what sort of devastation they had in areas like Mexico Beach and Panama City. And this is not to mention recent intense storms in other parts of the world. And so today what I want to talk about is some of my research on the basic physics controlling tropical cyclones, what tools we can use to make projections about future tropical cyclone activity, and given that, how is climate change expected to affect tropical cyclones? So I want to start off first with a few definitions. A tropical cyclone, that's the general term for this type of phenomena. In the Atlantic, we usually call them hurricanes. In the Pacific, they call them typhoons, but it's all the same physical phenomena. They're just different words that we use. And so a tropical cyclone is a warm core, meaning that the temperatures are warmer at the center of the storm than they are at the outside. Non-frontal, meaning it doesn't have cold and warm fronts like winter storms do. Rotating, it spins, organized system of clouds and thunderstorms that originates over the tropical ocean. And so this general term tropical cyclone also includes several other classifications based on the strength of the wind from tropical depression all the way up to major hurricane. Now, other than this structure, which I just mentioned, what distinguishes tropical cyclones from, say, mid-latitude winter storms, which are also cyclones, is where they get their energy from. And so tropical cyclones and hurricanes get their energy from the ocean surface via evaporation, which transfers heat energy from the ocean to the atmosphere. And so this is driven by a temperature difference between the ocean and atmosphere, essentially. So that's the definitions, and I'm going to kind of use the words tropical cyclone and hurricane, or sometimes TC for short, interchangeably. Now, since we're going to be talking about how climate change affects tropical cyclones, I want to talk a little bit about how we make tropical cyclone climate projections, what sort of tools we use. The first one is our expectations from theory. If we have physical theories for what controls tropical cyclones, their intensity, how many of them form, we can then see what those theories tell us should happen if we have a warmer climate. And we have theories for some aspects of tropical cyclone activity, but not for others. And so we also need to rely on climate models. A climate model solves the equations of motion that govern how weather systems form and move in the atmosphere. They also have representations of how the ocean circulation works, how the land surface evolves and interacts with the atmosphere and ocean. And so they really are representing all the different pieces of the Earth system. And over time, they have improved in their skill and ability to represent tropical cyclones. It's a hard thing for them to do because tropical cyclones and hurricanes occur on relatively small scales compared to the whole Earth that we're trying to model here. But the models are getting better and can now represent the climatology of tropical cyclones with some fidelity. That being said, there are biases that remain, and so some of the work I'm working on now is to identify these biases in climate model tropical cyclone representations and identify how we can improve them and what errors are leading to those biases. And so this is just an example. This shows all of the hurricanes in this top left plot here, all of the hurricanes that formed around the world in a 5-year period. So all the little dots are where an individual storm formed, and you can see that they form across the whole global tropics, more or less. And then the other panels here are 5 different climate models who are trying to represent the same thing. And as you can see, they do a decent job in terms of putting hurricanes in the right places and having, in some cases, about the right number of them. But they're not perfect. There's clearly some biases. In general, they have too few storms in the Atlantic, like this model does, or too few storms overall. But this is still good enough to get useful information about them, but it's clearly not perfect. Something else that models struggle with particularly is getting the intensity of storms right. In particular, because these climate models need to run for hundreds of years, they have to use very large grid spacing in order to make that computationally feasible. And that makes it difficult to resolve the most intense storms, like this Category 4 storms I was just talking about. And so this shows the distribution of intensity of tropical cyclones simulated by these models. So this is over many, many storms, not just a single storm. And so these Category 4 and 5 storms I was talking about before, they're up here at the right end of this distribution. And the dashed line shows what this should look like in observation. So we have a range of different strengths of storms. All the colored lines show different climate models. And as you can see, at least amongst this set of models, none of them really get the most intense storms here. These the red and the orange one here, they come the closest and they have the most intense storm. And the reason is because those two models have higher resolution than the other models. But all of these other lines, these are all models that have the same resolution, and they clearly still have differences in how well they can represent this distribution. And so, for example, these two models produce much stronger storms than these two, even though they have the same size in their grid spacing. And so the resolution is not the only thing that we need to get a good simulation of tropical cyclones. And so what I'm working on is to identify the physical processes that are responsible for this difference between models in terms of how well they're able to simulate tropical cyclone intensity. And these are things including how clouds and moisture interact with each other in the atmosphere, and they're processes that we can then target specific areas for model improvement rather than just saying, well, the models are bad, but we don't know how to fix them. It's trying to figure out how to fix them. And so we have a lot of, we're really excited about that project and the applications from it. Now, so we can get some information from these climate models about how things might change if you take these model simulations and run them in a future climate with increased greenhouse gas emissions, for example. But since they do have some issues remaining, there are other tools that we use as well. And so since climate models have a hard time simulating tropical cyclones properly directly, what we also often do is look at changes in the large-scale environment that are predicted by the climate model. So this would be like how the sea surface temperatures over the Atlantic basin change, how the humidity in the atmosphere changes. So kind of large-scale environmental things. And then we can take those and do several different things to infer tropical cyclone activity based on that. And so we can use statistical relationships between the large-scale environment and the TCs to infer how TC characteristics might change. We can also use those large-scale conditions from the global climate models to drive higher resolution models that do a good job simulating tropical cyclones. And so these are what are called downscaling approaches, is how do we take this kind of coarse, approximate information from the climate model and get detailed specific predictions. And these methodologies are improving all the time, but they do all have some uncertainties associated with them. So now I want to talk about if we apply some of these methodologies along with our basic physical understanding of tropical cyclones, how do various parts of their characteristics change in a warmer climate. And so I'm going to talk about the frequency of tropical cyclones, which is how many storms there are in a given year, the intensity, which is how strong the winds are, as well as some impacts, including storm surge and flooding from rain. And so first I want to talk about tropical cyclone formation. And so before we can think about how the frequency of storms might change in the future, we have to think about what controls tropical cyclone formation in our current climate. And so our understanding of tropical cyclone formation is that there are several favorable environmental conditions that are necessary. In particular, because TCs get their energy from the ocean surface, you need warm sea surface temperatures, basically in the current climate above 80 degrees or so, in order for the tropical cyclone to form. You also need high relative humidity in the atmosphere, and that's because tropical cyclones are systems of convection, right? They're these thunderstorms that are rotating around in an organized circulation, and thunderstorms like occurring in humid air. You also need what's called low vertical wind shear. Vertical wind shear is the change in the wind speed direction with height in the atmosphere. And so if your winds higher up in the atmosphere are blowing, for example, faster than your winds close to the surface, this can make your storm asymmetric and kind of like lop the top off of it. And that makes it really hard for them to get their act together and form and intensify. And then the final thing is, because these are rotating systems, we need some amount of ambient rotation in the atmosphere. And so that's why these storms don't form directly on the equator, because there's not enough rotation there, as we saw in the plots from before. Now, these are all necessary conditions, but they're not sufficient. You still need some sort of trigger mechanism to get things started. And once that happens, then we can think about how many storms there are in a given year and how that has changed. So this just shows from 1988, I think, to 2007, the number of tropical cyclones per year. So the total height of this bar is the sum globally, and that's around 90 tropical cyclones per year. And we can see that there's no trend in that number, including if we look over longer time periods. The different colored bars are breaking it up by different regions in the world. So the Atlantic is this yellow kind of whitish one here. And one thing to point out is that, obviously here, living in the United States, in Florida, we hear a lot about Atlantic hurricanes. Rightly so, they're the ones that are affecting us. But the Atlantic is a small fraction of the world, and it only contributes about 10% to the total global tropical cyclone activity. The Pacific is the dominant player, and so I think it's important not to forget about the rest of the world when we're talking about tropical cyclones. Now, it would be really great if we had a theory to predict this number, because then we could apply an increase in temperature to that theory and know what would happen in the future. Unfortunately, we don't have that theory. We do not know what sets this number here. We don't, why is it 90? Why not 50 tropical cyclones here? Why not 500? That's a gap in our knowledge, and that's one that my research is working on trying to fill, as well as many other people around the world. But given all this, how do we expect the number of tropical cyclones to change in the future? Well, climate models project that there will be either a reduction or about no change in the total global number of tropical cyclones. But this is very uncertain because, as I just said, we don't have a theory for what determines this number. And climate models, while improved, still have biases. And so, we only have one line of evidence, and it's a line of evidence we don't particularly trust very much. And so this is certainly an area where a lot of people are working to try to improve both our theoretical understanding of what controls hurricane formation, as well as the climate model, so that we can have a more certain answer on this question. So that's in terms of the number of tropical cyclones. How about the intensity, the strength of the winds? Well, for this, we do have a theory, which is great. It's called the potential intensity theory, which is a theory for the maximum possible tropical cyclone intensity. So you think of it of kind of a speed limit for the tropical cyclone winds. They can't get higher than that speed limit. And that speed limit is determined by thinking about the hurricane as a heat engine. And so as air flows into the center of the storm near the sea surface, it picks up energy from the sea surface, from those evaporation fluxes. It then rises in these deep convective clouds near the eye wall, and transport heat in the vertical, and then far away from the storm, the air sinks back down. And so this cycle of energy around the storm, you can calculate how strong the winds that would result from that cycle of energy should be. And they depend on the difference in temperatures between the sea surface and the atmosphere above the sea surface. So if you have a bigger difference in that temperature, you have a stronger storm. And so we can apply this to the climate change problem. And what happens? Well, we find that in the future, we expect that there will be an increase in the frequency of the most intense TCs, so more Category 4 and 5 storms. We also expect that the average strength of the storms will increase, and that follows from an increase in this potential intensity, or this speed limit of tropical cyclones. And this prediction is supported both by theory, our basic physical understanding that I just explained, as well as model projections. And so we have two lines of evidence, and so we have more confidence in this than we did for how the number of tropical cyclones would change. And so this is just an example of how this speed limit on tropical cyclone intensity changes in the future. This is a map of the future potential intensity minus the current, and it's basically red everywhere that tropical cyclones form, more or less, suggesting the speed limit is increasing everywhere, and so hurricane intensity would increase as well. And so it goes up by maybe 5 to 10 meters per second, so there could be a substantial increase. Okay, so that was intensity. How about some of the impacts of tropical cyclones? One of the biggest impacts is via storm surge, which is responsible for a large percentage of structural damage, flooding, and unfortunately loss of life. And what storm surge is just an increase in the sea levels at the coast as a hurricane approaches. And so this is caused simply by the winds of the storm pushing the ocean water towards the shore as the hurricane comes closer to land. Additionally, since in the center of the storm you have lower atmospheric pressures in the eye of the hurricane, that causes the ocean to rise as well. And so it's this combined sort of just increase in water levels as the storm is approaching. And then of course you have waves and everything on top of that. The amount of storm surge that you get depends on the strength of the wind, so stronger winds pile up more water. It depends on the size of the tropical cyclone wind field. So if you have winds blowing over a larger area, then that can pile up more water. And at a specific location, it depends a lot on the shape of your coastline, the bathymetry underwater, the topography right at the coastline. Does it stay flat for a long time, or does it increase rapidly? So for example, around here, Appalachia Bay is this concave shaped bay, and that can kind of like funnel the water in together. And so our area is actually very vulnerable to storm surge. Now, given all this, that it depends on these details, it's hard to say how that might change in the future, but what we can say is that the impacts of storm surge are expected to increase because of sea level rise. So in a warmer atmosphere, we have higher average sea levels, and that means that any flooding that would happen from storm surges are adding on top of already higher water. So the impacts would be worse. And so this just shows that on average, there's already been 1/3 of a meter, so about a foot of sea level rise, and more is expected in the future. And this is a very confident prediction. The last thing I wanted to talk about is rain. And so in addition to flooding at the coast from storm surge, you can have inland flooding from amounts of rain, and that's what we saw happen in Hurricane Harvey and Hurricane Florence recently. And so what determines how much rain a tropical cyclone produces? Well, we have more rain for stronger rising motion in the tropical cyclone. We have more rain if there's more moisture in the air. So more moisture means more of it can fall out as rain. And we also have more rain for a deeper, taller cloud. And so this is showing Hurricane Michael as approached, and the colors here are the amount of rainfall from a radar image. And so this ring of very intense rainfall surrounding the eye of the storm is because that's where the strongest rising motion is. Now, on top of this, at a given location, the amount of rain depends on how slowly or quickly the storm is moving. So if it stalls and just sits in one place for a few days, you're going to have a lot of rain. And recent results have shown that globally, the speed at which tropical cyclones move is actually decreased. It's decreased by about 10%. So they're moving more slowly, which suggests there might be more potential for these extreme flooding events. How do you expect rainfall to change in the future? Well, we expect the amount of rainfall produced by tropical cyclones to increase, and this simply follows from the fact that there is more moisture in a warmer atmosphere. And this is Again, a very sort of fundamental response that's supported by both theory and model projections. And if the storm motion, the speed of that continues to decrease, that would compound this moisture-driven increase in total TC rainfall. So with that, I'll end and just summarize what we think our understanding is in terms of future projections of tropical cyclone activity. From most confident, which is that storm surge will be worse because of sea level rise. We also expect rainfall and TC intensity to increase, but we're less confident in how the number of storms would change. And some work that I'm working on to try to improve our understanding and these projections is work towards a better fundamental understanding of how hurricanes form and what determines how many we get, knowledge of what allows for a good climate model simulation of TCs, and efforts to improve that in the future. Thank you very much.